Okay, the project that I'm presenting here today is a collaboration between the University of Central Florida and the South Florida Water Management District. The work that I'm presenting has been done by my postdoc, Robert Jane, and it also included myself and our colleagues at the district, whereas Obi, who used to work at the district, is now a professor at FIU. So this project is about assessing compound flooding from different drivers: rainfall, storm surge, and groundwater table in South Florida. When we talk about compound flooding in coastal areas, we are usually concerned about these different flooding drivers to coincide, including the oceanside water level that is comprised of storm tides and waves, extreme precipitations that can lead to runoff, river discharge, and also sea level rise plays an important role, not just because it pushes the storm tides upwards, but it also affects the groundwater table, another driver of compound flooding that has often been ignored. And the whole topic of compound flooding or compound climatic events in general had a lot of attention over the last couple of years, and I just list a few papers here at the bottom that are all more like perspective articles where you would find more interesting references. The overarching goal of our project was to assess the effects of compound flooding in South Florida and how it can affect the design and the flood protection level of service assessments that the South Florida Water Management District is conducting on a regular basis. You can see here an example of one of the flood protection structures that they are managing. And those are designed based on upstream and downstream boundary conditions, including river discharge, rainfall upstream, and storm tides downstream. The phase one of the project started in 2018 and finished last year in 2019. We split it into different tasks: literature review. We developed a statistical approach to assess compound flooding effects. So we are working with statistical models here, as opposed to numerical process-based models, which can also be used, of course, to assess compound flooding, but are often computationally a lot more costly. We collected data from the different case study sites that we identified, and then we applied the statistical models that we developed in task 2 to these data sets. We just started with phase 2 of the project. I won't go into details here, but I'll come back to that a little bit later on when I wrap things up. The team composition, our stakeholder partners, of course, district staff. Most of them have a background in civil engineering, especially hydrology. Academic partners at UCF, Rob Jane and myself, also background in civil engineering, whereas Rob's undergraduate degree is in mathematics and statistics. And I usually consider myself a hybrid civil engineer / physical oceanographer. So those are the expertise, or this is the expertise that we have on the team. And so far, we feel that we cover all our bases for the project, at least the goal that we have in mind. How did we engage with the stakeholders? Importantly, I started conversations with Obi quite early about compound flooding in general. We had discussions on and off, and he was still at the district at the time. Before he left, we then initiated phase 1 of the project because there was a clear need or a clear interest from the district side to work more towards the incorporation of compound flooding into their risk assessments. And that's exactly what we were doing in my group as well. So it made sense for us to sit down, and we developed this scope of work document from the bottom up. We then had a kickoff workshop in person where we discussed different key aspects of the project: the case study, locations, data availability, how we would exchange data, statistical model design, and so forth. We then had regular update calls throughout the project, a final workshop where we presented results to a wider group of district staff, not just the few people who were directly involved in the project. And then we started co-developing scope of work for phase 2 of the project in a similar sense as we did for phase 1. The study sites here shown in Miami-Dade County, one in the southern part, middle part, and further north. In all cases, we picked a structure that is managed by the district. And then for each of these structures, we identified rainfall data from a close-by rainfall gauge. We selected downstream data from tide gauges representing the oceanside water level or the storm tides. And groundwater table was also an important variable for us to include. So we also used data from that. And you can see here in the lower left that some of the records are quite long and others not so much. We then started performing a bivariate analysis, going through the different steps that one typically has to consider when performing such an analysis: data pre-processing, identifying extreme events, a sample of extreme events to first get a sample of data that we actually want to analyze with our statistical tool. And here we use the two-sided sampling approach, where we first identify all the events where the rainfall was extreme and the coincident storm tide or oceanside water level, and then the other way around, we picked the extreme storm tide values from the data set, and then identified the coincident rainfall values. And this gives us these two samples here, shown as the red crosses and blue circles. Then we have to identify suitable joint distributions to model the dependence between these variables. So here we are dealing with a bivariate analysis, and we are dealing with data sets that are not independent. There is correlation between storm surge or storm tide and rainfall in this case. They are not fully independent. They are also not fully dependent, which is what the district currently assumes in their risk assessment, which is overly conservative in most cases. And we used copulas to model this existing dependent structure between the variables. Copulas are very flexible because they preserve the dependent structure between the variables of interest, while also being able to capturing the marginal behavior, the behavior of the individual variables that are included in the analysis. We then obtain a contour line or a quantile isoline that is shown here in yellow with some red. So everything, or all the event combinations on this quantile isoline would be considered, in this case here on the left, 50-year events of joint rainfall and storm tide. And we use the and joint return period, meaning that we are looking at the probability that both variables are extreme at the same time. We then can look at the density along this quantile isoline, which is the red shading here, to identify what we refer to as the most likely design event. So along this contour line with an infinite number of event combinations that are all considered 50-year event combinations, we identify the one that occurs here at the highest density along this isoline, and that allows us to directly compare our result from this flexible statistical analysis with the approach that is currently used by the district, assuming full dependence between rainfall and storm surge, meaning that we assume that every time there is a 50-year storm surge event or storm tide event, there would also be a 50-year rainfall event. And you can see that this is very conservative. It's far outside the quantile isolines that we come up with here. And we then could see, for example, how long it'll take for this gap between the black diamond and the black triangle to be closed. So at some point they would intersect on this horizontal line here, because we know that the oceanside water level distribution is shifted upwards because of sea level rise. So we looked at different sea level rise scenarios to see how long it will take before this safety margin that the district currently includes implicitly into their design will be used up because of sea level rise. And that depends very much on how fast sea level is going to rise in the future. We looked at different scenarios from NOAA, and you can see that the time it will take for the safety margin to be exhausted can be anywhere from a few years under a high sea level rise scenario to many decades under a low sea level rise scenario. We then extended the analysis to the trivariate case. I mentioned at the beginning that we wanted to include the groundwater table as a third variable, which is also correlated, of course, especially to rainfall, a little bit also to storm tide. And we used, again, different models, more complex models that allow us to go beyond the bivariate analysis. And we found that some models are more appropriate, obviously, than others. The vine copulas, for example, performed relatively well, and especially the Haffen and Thorn model, another flexible multivariate model here at the bottom that captures the correlation between the different variables quite well and also preserves the marginal information. I won't go into more details here from the three-dimensional analysis. That would take too much time. I would rather summarize a few of the successes and challenges that we so far experienced. Successes, I would certainly say we now speak the same language. It took a meeting or two before we really were able to manage our expectations, get on the same page, what we want to achieve, what we actually can achieve, and most importantly, to build trust between us and the stakeholders. We co-authored a paper together led by Rob Jane, which is currently under review with NHAS has been resubmitted, should hopefully be available soon, along with the R package that we developed as part of the project. And we also started training the district staff on using this R package. In phase 2, and that summarizes some of the challenges, we want to update the tool to build in more options, more flexibility for the stakeholders to use different setups of the statistical analysis, always having in mind the trade-off between developing something that's very user-friendly, but then is only a black box, or something that is very flexible, but then it may need a true expert to be able to run it. So we want to end up somewhere in between. And that will definitely also include some more in-depth training that we will provide to district staff on the theoretical background of multivariate statistical analysis, which is not a field that most people have dealt with a lot, and also in implementation of the code, application of the code, and especially the interpretation of the results. And then, as always, when performing statistical analysis, there is limitations in terms of data, and that is particularly important when assessing compound flooding, because then we need co-located data from the right places and relatively long records that should overlap in order to capture the correlation structure and then model it appropriately in the statistical model. And I'll stop here. Thank you very much.